Good afternoon and welcome to the Center Stage Seminar Series event. My name is Tiffany Willoughby, Education Programs and Outreach Manager in the Office of Research at the University of Texas at Dallas. I will be your moderator. Joining me today is Dr. John Hansen. John H.L. Hansen received a PhD and MS degree from Georgia Institute of Technology and a BSEE degree from Rutgers University. He joined the University of Dallas Erik Jonsson School of Engineering and Computer Science in 2005, where he is currently Associate Dean for Research, Professor of Electrical and Computer Engineering, Distinguished University Chair in Telecommunications Engineering, and holds a joint appointment in the School of Behavioral and Brain Sciences, Speech and Hearing. At UT Dallas, he established the Center for Robust Speech Systems, CRSS, including Robust Speech Technology Lab, Cochlear Implant Lab, and UT Drive Labs. He is an ISCA Fellow, IEEE Fellow, past member and TC Chair of IEEE Signal Processing Society Speech and Language Processing TechCom, SLTC, ISCA Distinguished Lecturer, and served as Technical Advisor to the U.S. Delegate for NATO. He currently serves as ISCA President. He has supervised 91 PhD MS thesis candidates, was recipient of the 2020 UT Provost Award for Graduate Research Mentoring, 2005 University of Colorado Teacher Recognition Award, and co-author of 753 journal conference papers, including 12 books in the fields of speech and language processing, assistive hearing technology, and driver modeling. He served as General Chair and organizer for ISCA Interspeech 2002, co-organizer and technical program chair for IEEE ICASSP 2010, and co-general chair and organizer for IEEE workshop on spoken language technology. He is serving as tech chair for IEEE ICASSP 2024 and co-organizer for ISCA Interspeech 2022. Please join me in welcoming Dr. Hansen as he takes center stage in the spotlight. Dr. Hansen, welcome.
Thank you very much, Tiffany. This is John Hansen. I greatly appreciate the opportunity to talk to the UTD community about research and activities here at the Center for Robust Speech Systems. So today I'm going to give a brief overview of different aspects relating to robust speech systems. The Center for Robust Speech Systems is a collection of various laboratories: the Robust Speech Technology Laboratory, the Cochlear Implant Processing Lab, and the UT Drive Lab. These three labs I oversee and coordinate students and staff members in those areas. Chin-Tuan Tan oversees the Auditory Perception Lab, and Dr. Carlos Busso oversees the Multimodal Signal Processing Laboratory and has an extensive number of students and staff members in his lab as well. Previously, Yang Liu oversaw the Speech Understanding Laboratory in Computer Science. She's since moved on to other activities in industry. And our previous colleague, Philip Luizo, oversaw the Speech Processing and Cochlear Implant Lab before unfortunately passing away in 2012. I'd also like to recognize Raja Razakarian, who's a senior lecturer and faculty member in the ECE department, who's been a long-standing supporter of all of the different students in these various labs that make up our center. So in moving forward here, what I'm going to do is to try and highlight a number of different aspects. These are the students that are currently supported in the three labs that I work with: the Robust Speech Technology Lab, Cochlear Implant Processing Lab, and the UT Drive Lab. So most of these students are working at different aspects, research pieces. All are PhD students that are focused on advancing various technologies that improve speech systems for interactive computer interactive systems, as well as forensics and child-based interactive solutions. In addition to the Robust Speech Technology Lab, I'll mention we also have the Cochlear Implant Processing Lab. 6 students are involved in that laboratory. And finally, in the UT Drive Lab, we also have activities on driver modeling and distraction there. Over the years, we've had a number of staff members. Finian Kelly is one of our staff research scientists that's been with us for a number of years, and a number of adjunct faculty members. These actually all were previous postdocs or research scientists that have been with us for a number of years. And over the last maybe 10 years or so, we've employed a transcription staff of anywhere from 2 to 4 students, mostly from brain behavioral sciences, that have been involved in supporting our research activities. Now, I'd like to kind of just highlight, we were established in 2005, so we've been here for 15 years. So in the 15-year history, we've accomplished quite a bit. So I'd like just to highlight a number of the advancements that have taken place over the last 15 years. So, I'm an engineer, so I tend to kind of put things in tables and so forth. So and no one can read the details in there. So I'll just highlight a couple of things. First, we've supported many PhD students. So over 300 PhD RAs have been supported over the last 15 years, averaging roughly a little over 20 PhDs supported per year as RAs in these 3 different labs. We also strive to have strong diversity in our representation here. So roughly about 1/4 of all of the postdocs and PhD students are women. In our postdocs, we've typically had anywhere from 2 to as many as 5 postdocs supported in the lab. They work closely with our students and help mentoring the students and the research projects. In the last 15 years, we've completed 38 PhDs, averaging roughly 2.5 PhDs completed per year. As you can see here, a healthy balance in gender. And as well, we also have a number of master's thesis students that have also been completed over the last 15 years. In terms of publications, 116 publications over the last 15 years, averaging 8 journal papers a year, and roughly 400, a little over 400 conference papers, around 27 per year. So these represent all the students and staff members that have been involved in these 3 labs, working diligently to kind of address some very challenging research problems. So moving forward, we're going to look at each of these labs briefly and kind of highlight some of the research activities. So I'm going to start off with the UT Drive lab. So when we look at driving, one might ask, well, how does speech play a role into this? Well, clearly people have tried to bring in their cell phones and to use smartphone technologies in the car. But if we look inside a vehicle, people do a lot of different things other than just operate their vehicle. So you can see everything on the left here identifies all the different types of secondary tasks other than driving the vehicle that people attempt to achieve, if you will. And there's some challenges that involve with that. Unfortunately, people have spent time using their cell phone when they shouldn't. Texting is clearly a major security or safety issue that one would see in the car. But other secondary tasks are also an issue. Looking at what are some of the challenges there, we established in 2005 with funding from NETO. It was a funded project from Japan after we received DARPA support for smart vehicle systems to establish the UT Drive instrumented vehicle. So this was bought by UTD on one of our projects. We instrumented this vehicle. There were basically 3 senior design teams that helped instrument this. And this has been on the road for the last 15 years. We have instrumented sensors that are distributed throughout the vehicle, cameras that look to see what the driver is doing as well as where the driver is going. And so this system has been on the road and has collected many miles of driver data that have been used to model driver distraction, driver characteristics. In addition to that, we felt it was important to try and migrate away from instrumented vehicles. So we've also established the UT Drive mobile app. So this is a smart platform that allows you to download into an Android smartphone or tablet and emulate everything that the instrumented vehicle will have. So if you've got a son or daughter that's going off to college this fall and you want to get access to our Drive app, you can now actually monitor exactly how they're driving continuously. And while this may actually be used by some insurance companies today, this was fairly revolutionary about 10 years ago when we first put this together. So we've shared this Drive app with a number of different groups. In addition to that, we've also been actively involved in the field for driver modeling, driver safety. Every 2 years, we've had a workshop that has been organized across the world in the United States several times, in Portugal, also in Germany, in Japan, and in South Korea. In addition, when we hosted this workshop here at UT Dallas in 2009, we are fortunate enough to have Bruce McGladrey as one of our keynote speakers. Here's Bruce actually driving the UT Drive vehicle, and Bruce at the time was the director of the National Transportation Safety Board. So quite nice to actually have the person responsible for overseeing safety for all transportation in the United States driving the UT Drive vehicle. Interestingly enough, not to play politics, but the NTSB is the only government agency that does not report to anyone else. They're completely independent and do not have any political persuasions per se, I'll put it that way. So their main focus is to assess accident causation and to provide feedback to try and improve safety. So Bruce was very interested in seeing the work that both UTD and a variety of other collaborating institutions have put forth on driver modeling and driver behavior. In addition to that, I'll show you some data we've been collecting. So this is the instrumented UT Drive vehicle along with the mobile UT Drive app. Here are just several routes that we take around the Richardson area. We've driven many drivers. We have a core corpus of about 150 drivers driving multiple times to be able to get access to that data. In addition to that, we can look at driving behavior of different drivers. So when we collect the we collect the data, we actually get where the driver sees and what the driver is actually doing. So that comes from the cameras as well as the mobile UT Drive app. Variety of different sensors that are captured by the mobile app, as well as the CAN bus, which is the electronics that come out of the vehicle. So we can compare the smart app along with the CAN bus data analytics to be able to determine whether the app is able to reflect what the instrumented vehicle will give us. I will point out that these two drivers, even though I'm showing their faces, they are, I would say, captive drivers because they're my twins, my daughter and my son, and she just graduated from UTD here in May and is going on to do her PhD in about 2 weeks. My son, a little bit behind, but he's going to graduate as well. So from here, we can see that we can collect large amounts of different types of data. This shows some of the different types of characteristics when people drive. So here we're showing steering wheel angle, speed, and braking characteristics. So if you're making a right-hand turn or a left-hand turn, clearly steering wheel angle would be the primary metric that would change. And you can see for the left and right-hand turns, those do change. In lane keeping straight, where you can see the speed is the variable that's carrying on there. The speed for left and right-hand turns are not changing so much, but the speed on lane keeping straight is. We can see for lane curves, if you're driving and making a curve, you can see there's some variability in here. But if you're looking at all the maneuvers, the one maneuver that changes or has the most variability is this maneuver called stop. And so you might ask yourself, well, why do I see such a wide range of steering wheel angle, speed, and brake activity when the person is supposed to be stopping? And the reason is because people don't actually stop. So on average, a person drives through a stop sign roughly about 2.1 miles per hour. So you actually don't technically stop. So if you're driving on campus late at night and you see a UTD police officer, make sure you actually come to a complete stop because they can actually tell if you're going too fast. And so this is actually particularly important in modeling driver behavior, because now we can look at the dynamics and the variability of how someone drives to see whether they're moving into a risky situation. And that might be something that we might want to communicate to other drivers or to the infrastructure to try and help improve safety for everyone. So this kind of shows an example of driving a driving path. We pull the data out of the CAN bus system, and we analyze the driving characteristics from the vehicle, And we can build models for how you would drive this particular route, and then look to see if there are any areas where you might be driving in a risky scenario. And you can see here that we're able to mark what might be safe, moderate, and risky driving in different locations here. So with this, we can kind of identify clearly some spots here on campus where the person driving probably needed to kind of slow down or not move as quickly as they could. And in a different aspect there, one could also look to see if you're driving without a task. These are individual drivers, and based on the assessment strategies, we can see what their range of operation are. So some drivers here typically are either distracted or maybe somewhat risky even without a task. And when we introduce the task, they become even more distracted. So the issue here is that when you add an additional task to your driving, you're more typically doubling the amount of risk factor that you have when you're driving. So always be careful if you're driving. If you get a cell phone call or a text message, please just set it aside. It can wait until you pull over and be able to respond to that. But here we show actual characteristics of drivers as they change because of a task. So that gives us a little bit on the UT Drive activity. In addition to this, we also look at some future directions here. So one of the things we're focused on are some of the deep neural network strategies. One is to look at transfer learning. And this is particularly important because we can capture data from a particular core set of drivers and be able to now build a model and apply those models to new drivers to be able to come up with predictive ways of trying to characterize when a driver might be moving into a risky scenario. So looking at sequences of images as well as taking CAN bus type data, we can build effective deep neural network models to characterize these things. We have network features that come out, and from that we can develop machine learning strategies using recurrent neural networks or long short-term memory modules-based systems to assess driver risk. In addition to that, one could also look at trying to characterize also risk factors based on the vision aspects there. So looking at lane keeping and determining where a vehicle might be cutting into your lane or whether you're making a lane change, would that make a factor? So today, smart vehicles would allow us to be able to take that type of information, similar to what we show up here, and develop strategies to give feedback to the driver to lower their risk factor, especially if there's high traffic or if environmental or weather conditions actually cause challenges for the driver. So this gives kind of a brief overview of the UT Drive Lab. And so at this point now, I'm going to shift over to the cochlear implant processing lab and give some updates from that space there. So the cochlear implant processing lab, this actually grew out of the pioneering work of Philip Luiso, who pioneered the field of signal processing for cochlear implants. He single-handedly established, I believe, the main research field that uses implant or signal processing in implant strategies. Previously, most work focused a bit more on the science, and Philip looked a lot at the signal processing aspects. When he passed away in 2012, we ended up receiving, unfortunately, his staff and students, roughly 10 people in his group. And so we moved them forward, and over the last maybe 8 years, we've been able to bring in some new additional funding from NIH to follow up on his initial pioneering work. And that's resulted in a new design for cochlear implant research platform that we have. So this is funded under an NIH R01 that is now finishing its second year. And so let me first just mention, when I'm looking at hearing aids are obviously an electrical device that captures audio, processes it through some system, usually a behind the ear or in the ear type system. This is the processing pipeline here. It provides amplification and compression of the input audio in order to improve intelligibility and quality for people with hearing loss. If someone has greater than, let's say, 75 to 80 or 85, 90 dB hearing loss, then one is typically a candidate for a cochlear implant. And in that case, an electrode array is surgically implanted into the cochlea, typically to stimulate either the vascular membrane directly through the inner and outer hair cells, or spiral ganglion cells, which are connected to those hair cells. And so when looking at a cochlear implant, you're actually transforming audio information through a signal processing strategy to a series of electrical pulses that are transmitted through an RF coil to a receiver coil that's surgically implanted inside the person. And so it's that receiver that actually picks up the processing strategy. The challenges with cochlear implant systems is that roughly only about 5 to maybe 10% of the actual acoustic data makes it into the stimulation pulse train. So we have to come up with clever, creative ways to try and give cochlear implant recipients better characteristics to try and improve both intelligibility, speaker identification, as well as quality of what they're listening to. So the research platform that the CI lab has developed is shown here. This was designed from the ground up. So the entire hardware, software, and firmware was completely designed here at UT Dallas from scratch. And so we produced this device. You can see we actually even do 3D printing. And so this device is set up to basically facilitate research support for the cochlear implant research community. All the software is open source. It allows people to download and freely use the software materials. The hardware obviously has a cost, and so we license the hardware in order to cover some of the expenses and to try and support hardware to research laboratories in the field. So to look at this, the processing platform, again, you start off with an acoustic waveform here. There's a processing pipeline one goes through in order to extract the important information, either the text or speech content, looking at the type of channels that need to be stimulated, developing an electrodogram, which is shown here, that actually shows the mapping of what electrical information will be stimulated to the inner ear. And what our goal is to try and come up with strategies that allow us to take the most salient points of speaker, text content, and acoustic characteristics of the input signal and represent them as best as possible in this output electrical stimulation pattern. So this represents the research platform. You ask, well, why would we need this? Well, the reason is because there's basically 3 main cochlear implant manufacturers, and unfortunately, it's very difficult to test drive new programs. And so the research platform here facilitates that. People can basically load their software either on smart tablets or on PCs and be able to run their systems with existing cochlear implant platforms. And that allows the person to basically do testing in the field, which is particularly helpful for research advancements. So this shows some of the software suites. We have a series of MATLAB software platforms that are freely available and downloadable on GitHub. We also have full support for Android, for smartphone or smart tablet type field use. And this has facilitated some really nice opportunities for testing in the field, especially now with COVID-19 constraints. It's now easier to go and test CI subjects without being in risky laboratory settings, per se. So this shows one of our CI subjects here on the UTD campus moving around. He's adjusting his processing map to maybe optimize for different locations. At this time, we now have over 20 of these units that are distributed throughout the world, mostly in the US, but Canada, Brazil, Belgium, Australia, China, and Croatia as well. We have several now that another batch of 35 units that we're looking to place here in the next year. I will point out that this is a really healthy collaboration with the University of Wisconsin-Madison, Ruth Lutowski, who heads up her team there, and Mario Zwerski, who's at NYU, also an excellent collaborator. Both of these teams have been extremely beneficial for UTD and allowing us to kind of leverage knowledge and expertise from the field. So that gives a brief overview of the cochlear implant lab. Now what I'm going to do is to shift over and kind of talk a little bit about the Robust Speech Technology Laboratory. Over the 15 years, we've accomplished and worked a lot of different problems. So I'm just going to highlight a number of the different areas just to give you a flavor for some of the problems that we've looked at. We look a lot at language ID. So we've done a lot of work on dialect ID here, looking at 5 different dialects of Arabic. We've also looked at speech under stress, so assessing military individuals in high stress scenarios. Roller coaster rides, we've collected a lot of speech in that area. We've worked for NATO. We've also done document expansion and query for audio document search here, and also processing for naturalistic audio streams. So we're going to highlight some of those. So in speech communication, one would say, well, if you look, the patent that has produced the largest revenue and is the single most cited patent on earth is the Alexander Graham Bell's patent for the telephone. But this setup has always assumed a one-to-one, person-to-person type communication. And today we're more likely to see group dynamics and group interaction. So it's much more likely to have groups working like we're having in this presentation and many people participating. So the future of speech communication and assessment is really not going to be so much a telephone call, but more naturalistic data capturing audio in real world environments, looking at multi-speaker content, maybe analyzing or building on big data, understanding STEM education, being able to integrate this into classroom settings, looking at team-based communications. And clearly one could also look at your home or going to any commercial store like Best Buy. You can find lots of voice-enabled and distance-based voice capture systems that give us smart home scenarios. So one of the aspects that represents a challenge going forward here in these naturalistic environments, you could see clearly many different types of voice entry or voice-enabled platforms here on the right. But we have speaker variability, and mismatch and variability is all over the place. We see from speaker, technology, and also conversational based. And all these variabilities kind of cause challenges for systems. So one of the areas we look at is in audio diarization. So audio diarization allows us to do speech recognition. One could also maybe kind of capture some of those words and maybe look at keyword spotting. The keyword spotting is particularly helpful if you're trying to identify maybe particular topics. Let's say if one is trying to look for sports or politics, you could look for certain keywords. Another aspect is looking at speaker tracking. So if you say, I have two people talking, I'd like to look at the dynamics of how they interact with each other, or maybe I'm looking at the environment. I like to characterize the environment acoustically. So there have been audio diarization techniques that have existed in the past, but virtually all of these always focus on a single channel in a short audio stream, typically, let's say, a lecture for an hour, or analyzing broadcast news or something on TV. Very few have actually looked at naturalistic data, and that's where the challenges really exist today. So this represents one corpus that we've been collecting for quite some time, since 2010, called the Prof Life Log. Basically, a prof, me, that wears this unit called a LENA unit. So this was actually developed by two of our students for the LENA Foundation. And this actually is used for monitoring and assessing child language, children from the ages of 8 months of age to 36 months. But I wear it typically once or twice a month for maybe more than 8 to 10 years, and analyze 16 hours of recording a day, and I can analyze what I'm doing, what I'm saying, and where I'm going. So a lot of my students analyze what John does, and so we have to have a diarization platform here. So to do this, we first run speech activity detection, then we extract what we think is the speech portion of that audio stream. We do speaker diarization. So from that, we're looking at the primary speaker and secondary speaker. If we're looking at the primary speaker, then we might feed that into a speech recognition system that's doing keyword spotting. So we can identify certain keywords that the person might be saying. In order to figure out what keywords you might want to recognize, you typically would have an offline resource generate what's called a bag of words that you might use then to feed into this keyword spotting system, and that would allow us to characterize certain traits about the diarization system. Now, to actually do this effectively, you need advanced models. I'm not going to, because of time constraints, I can't go into all the details here. But typically, building speech recognition or keyword systems, you typically might build a full model for one word. The problem with that is that you only really get maybe one pronunciation for a particular word, and that makes it quite challenging if you're looking at spontaneous or natural data. An alternative approach to modeling keywords or speech in terms of whole word models to look at something called phone confusion networks. And what these do is they allow us to maybe model individual phonemes or individual sounds that make up words. And now once we recognize those string of sounds, we can now have much better capabilities of characterizing speech if someone has an alternate pronunciation for particular words. That allows us to have much more flexibility. Very, very useful if someone has an accent, because this really allows us to characterize accent characteristics in a really good way. So we've used this to kind of characterize 16-hour audio streams that I use on a daily basis. And so here it shows the amount of time that speech might be active, either me or someone else talking. From the acoustics of the stream, we can characterize whether I might be in an office, inside the car, in a restaurant, or in a student union, or walking outside. And if I'm in group meetings, how much of the time I speak versus anyone else might be speaking. So we're able to detect that. And you notice here from a privacy perspective, we identify speakers based on generic labels and not names. So this way we can protect someone's identity. In addition to that, if you're looking at this audio stream, you'll see that we can detect when someone talks, and hopefully John is not talking all the time, and other people are speaking. You can see in this dynamic lots of variation of who's talking and where things are as we're moving along. So this is a nice way to maybe characterize your daily interaction. One might expect that, many smartphones today have a health app that can tell you how many steps you take. One would expect that future audio applications might allow you to characterize the number of words you might speak in a particular day. And so if you're asking that, this shows an example here of me doing a daily, not pre-COVID-19, on campus, and shows different days and how much of the time I was spending in different locations simply based on the acoustics, being able to characterize the environment that I might be in on a daily basis. And looking at where I might be located, how much of the time am I speaking versus someone else is speaking. And so hopefully, like in the lab, you can see I'm usually talking with someone, and half the time someone else is speaking and the other half I'm speaking. And maybe if I'm in the classroom, I do maybe more of the talking, but I do have students ask questions in the classroom. So you can see here, so if this was sitting way up here, no students would be asking questions. So at least students are asking questions there. But so in addition to that, one might say, well, let's go ahead and try to count these words. So this shows kind of the daily word counts. I think I have about 9 days listed here. And these show each day how many words are actually produced. So if you're trying to gauge, like, what is the typical number of words that you might expect that someone would produce in a day? Well, if you're looking at child development, typically 25,000 words per day is a healthy dosage of word exposure to a young infant or a child. So if you're out there and you have a newborn or a baby that is between, let's say, the ages of 6 months to a year, go pick up the Dallas Morning paper and read the paper to them. Doesn't make a difference that they understand. If they're able to hear those words, they're recording those. They're building that into their language system. And so exposure to that is really critical in looking at language development as well as intellectual development. Lena Foundation was the pioneers that focused on this. And you can see for me here, at least on these 8 or 9 days, there's some days I have light days. I only have maybe 6,000 or 15,000 words. And then there's days where they're pretty heavy. So I've got 52,000 words spoken on that day, 53 and 57,000 words spoken on that day. So on this one here, you can see it was a research meeting. I believe this was probably our Air Force sponsor in on that day. And so it was one of these marathon type presentations. Faculty meeting was the big one on this day, and some student meetings. So another challenge for that one. But this allows us now to look at how many words we speak each day and how we might be able to move forward in assessing communications. All right, so in addition to that, one could then look and say, well, can we apply this to other applications for education? And the answer is yes. So we went over to the Student Success Center and collaborated there with Nishan Jones, who was heading up the peer-led team learning space there in the Student Success Center. And we collected 2 semesters worth of STEM-based peer-led team learning sessions. So if you don't know, the Student Success Center runs PLTL program. Roughly about 85 teams are established each semester. It's almost like sleeping out for concert tickets for your favorite, musicians out there. Students gobble up those slots because they know that if they participate in peer-led team learning, on average, the GPA for that course goes up by 0.5. So what our goal was to see if we could use speech technology to try and assess and improve assessment characteristics of students working on either chemistry or calculus or other STEM-based type problem sessions that were going on. So in this setup, there's a PLTL lead and typically 6 to 8 students that are in the sessions. They're required to leave their cell phones out, although I see this one student, she left her cell phone there. She's not supposed to have it in there. And so we recorded the sessions with these little Lena units, and afterwards we actually went and analyzed all of the data coming out of those. So we did the analysis here, and this kind of shows for automatic labeling and human labeling, we could see the amount of time the PLTL leader is speaking in his or her recorder versus the amount of audio that is captured from each of the other students that were in that session. If we were to look at the recorder from student, let's say number 1, clearly that recorder would capture mostly student 1 and much less of the peer-led team learning lead. So this shows that we're able to do good characterization from that. So that shows an education type application. Now in the Robot Speech Technology Lab, another aspect that we look at is actually also in the speaker recognition space. This area is emerging. It's something that's really critical for both national security as well as for looking at different applications for electronic e-commerce and so forth. So in looking at the topic of speaker recognition, one of the big challenges that exists are the wide diversity of mismatch conditions. We tend to see mismatch due to speaker traits, and these are referred to as intrinsic speaker variability and extrinsic. So the intrinsic would be things like vocal effort. If you're whispering or speaking softly or loud, different types of style mismatch. So if you are under some type of maybe physical task stress, maybe you're physically doing something, or psychological stress or emotion, all these factors might change the way you produce speech. Another thing is if you're exposed to background noise, something called Lombard effect takes place. And that means that you're going to alter the way you produce speech in order to communicate more effectively over that noisy channel. So all these variations cause problems for speaker recognition systems. In addition to that, at least recently, people have attempted to try and look at non-speech vocalization. So these would be things like if someone is screaming, can you actually recognize who is speaking from a screen? And this part actually is really difficult. There's really not an effective way to do this. External type factors tend to be more related to what's called extrinsic variability. That would be like noise, reverberation, the room acoustics, different spaces that one would see. And so our team has been very active in this. We've collected probably about a dozen corpora over the last 15 years in these different mismatch conditions. We have this nice tutorial article that gives a really nice overview to the field, highlights a lot of work that's been done by many, many researchers out there, as well as a number of studies that we've done. So let's look a little bit at some of the forensic side. Before we do that, at least let's highlight what speaker recognition is. So typically in speaker recognition, one would expect that you may have models trained for individuals beforehand, and you have a voice or an audio stream that comes in. You're going to try to recognize it. Is it one of these individuals that you have models for? If you're doing something called open set speaker recognition, your goal is to determine if the person speaking is one of those members in your trained set, or if not, then you want to reject that. So you need another model that's called a world speaker model or an outlier type model. And so that's the typical approach that you would see for speaker recognition. If it's closed set, it's just those that you have models for. If it's open set, it would be these models plus the universal background model or world model. Now, another task in this domain is called speaker verification, and that occurs where someone is claiming to be someone, a voice input is given, claiming to be someone, and you have to verify, is that the right person, or should I reject that person? And this is particularly helpful if you're looking at providing services for this individual, if they're calling up and getting access to a bank account, or maybe getting access to medical information or something that you want to be held confidential or private, you want to verify that the person actually is who they say they are. And so voice is an ideal way to do this because it doesn't require any additional aspects there. So these are kind of two of the maybe 3 to 5 different ways that one might see for speaker recognition. In addition to that, one could also look at the content that's in your audio signal, and that plays another role in trying to understand speaker recognition. So clearly, one aspect is to look at the acoustic conditions. So that represents more of the physiological aspects of your voice system. In addition to that, one could also look at prosody, intonation. So these are some of the ways that you might actually produce a sentence while you're speaking. And then there's higher level type aspects, and these are referred to more as semantics, diction, or idiosyncrasies in your speaking style. So part of that might involve a particular phrase that someone uses quite often, or a particular pronunciation that someone might have for how they say a particular word or location or destination or something along those lines. And so for voice forensics, these are important. A lot of times people on the linguistic side will analyze these aspects. People on the speech technology side tend to kind of focus more on the signal processing, speech processing side, but obviously leveraging large amounts of different machine learning strategies to advance this. So now we've got a little bit of a background for what forensics and speaker recognition is. Today, if you're looking at different types of strategies for speaker recognition, clearly the advancements of machine learning, particularly deep neural networks, have been brought into play to try and advance these algorithms. You typically will see numbers of speaker recognition systems working in parallel, each having complementary type features or classification strategies to try and leverage strengths of one method over another. So this shows one example of a method using triplet loss with deep neural networks. And the pipeline that you see in this space here is actually inserted into this setup here. What a triplet system means is basically you're looking at the person you're trying to recognize, a model for the individual that you think is the model, and then a rejection model or universal background model. So what you're trying to do is to simultaneously measure how close is the unknown speaker to the reference model as well as to the rejection model. And that's what makes this strategy particularly helpful in trying to improve speaker recognition performance. So our system, or at least our center, has done a lot of work in this area. We compete in the NIST competitions worldwide. So NIST, National Institute of Standards in the US, provides a platform for evaluating speaker recognition systems. Every year they do an evaluation for language recognition, and the other years are done for speaker recognition. So they alternate each year. CRSS UT Dallas has finished quite well. We were third one year, losing only to a Russian company and a consortium in Singapore. So we were the #1 group in the US. This particular year in 2016, we finished 6th out of roughly 78 teams that were there. And these kind of show the performance of how groups worked. In 2018, we finished 4th, I think 11th and 15th. So we had submitted 3 different systems, and we also do collaborate with other labs to try and put in joint systems. So our systems are very competitive. We do really well nationwide. We are an academic institution, and obviously many of these competitors here are top research laboratories and companies that are competing in the field for advanced systems for the US government as well as for commercial applications. So one of the domains I mentioned was the application in forensics. And this is a real challenge today because there's lots and lots of domains where one might want to try and help law enforcement verify that someone is who they claim they are. And there are applications where trying to use speaker recognition is important. So there aren't many naturalistic data sets that are out there, lots of artificial data sets that have people that simply prompt speech. So they will read a sentence and then you're going to try to recognize whether that person is the same person. But many of these audio examples are kind of artificial. Someone's reading a sentence like, "She had your dark suit and greasy wash water all year." Not a sentence that you may actually say in general. So our group wanted to try and put together corpora that might be more useful to the forensic community. So we pulled audio from a TV program called The First 48, where we are now analyzing all of the audio from this crime show. It's a reality type crime show, and all the individuals, unfortunately, in this series, they represent detectives that you see here, and Unfortunately, what the first 48 means is that if you can identify a suspect within the first 48 hours after a homicide's been taken place, your prospects to solving the case improves by a half. So we're capturing actual suspects. Unfortunately, this individual was someone who committed a homicide, and so we're capturing all the audio, organizing it and using it, benchmarking to try and improve speaker recognition systems for law enforcement. We've also shared this data with a number of groups that are in the law enforcement and the forensics field. Another corpus that we've collected on campus involves looking at different environmental settings. So we've collected a large number of subjects in different locations, offices, in the hallway, lobby, anywhere on campus. And so we do that to get like field recordings for naturalistic interaction. So a person is interacting and talking spontaneously, and that allows us to get more natural sounding speech. We also do audio collection in a sound booth to have a more controlled scenario. And then to make this a real scenario that we might see in law enforcement characteristics, we actually engaged with the UT Dallas Police Department, and here is a detective for UTD Police who's actually interviewing one of our students who was helping with the organization here. But we had subjects coming in and they were actually interviewed by a UTD police officer in a make-believe scenario, whether something was missing, maybe a bicycle was stolen, and we're trying to determine whether the person has some knowledge about that. So the database also includes these types of interviews. So they give us a nice example of closed noise-free settings and sound booths, also field recordings, as well as actually being interviewed by a law enforcement detective in a scenario like this. So this will actually help benchmark a lot of voice forensic applications. It will also, in our mind, help reduce the prospects for false positives. So individuals that are not a suspect should not get a positive reading in these verification tasks. So trying to improve these technologies to do better in these open naturalistic settings improves the technology for law enforcement. So moving on here, I'm going to also highlight a couple of other applications that we've looked at for speech processing. So one of them is in this domain called co-channel or overlap speech detection. So we kind of know that if you have people that are talking, unfortunately, sometimes they may overlap. If you have two people that are speaking, in this case here, someone is speaking for speaker A, and then in this part of the audio conversation, both speaker A and B are speaking at the same time, so they're overlapping. So several of our students have been developing and advancing techniques to automatically detect whether we have overlap speech. Very important if you're trying to train speech recognition systems. You want to train a speech recognizer with audio like this. If you have overlap speech like this, you absolutely don't want to try and train a speech recognition system with that because it has now confusing text content in there. The same is true if you're trying to train speaker recognition systems. You now have two people speaking at the same time, so you really don't want that audio being used for training purposes. So a number of our students, we finished several PhDs in this area. One of them, we had done some excellent evaluations on available corpora out there, but I told them, look, you know, you really need to kind of show that this can be applied to a real world application. So I asked them, you know, to go and look at one task that I thought would be a real world application for overlap detection, and that was presidential debates. So we went and looked at presidential debates over the last, from 2004 to 2016, and under each of these debates, there's always three debates that take place in that year. So an introduction, the first debate, second debate, third debate, and what we do is we have our system that goes to detect the amount of overlap speech that might be present in that audio conversation between the two candidates here. And what we do is we see that it's typically about 2% for the first round. We can see for the second round, the candidates become a little bit more aggressive, so maybe from 2% to maybe 6%. And then, you know, the candidates don't want to be remembered as being too aggressive, having more overlap. And so in the third debate, they typically drop back and they're a little bit more respectful of each other and they don't overlap as much. And so this was the case for the 3 previous elections from 2004, 8, and 12. If we add up the amount of overlap here, you can see it's roughly about 10% over the 3 debates, and that's pretty consistent until the last debate, okay, from 2016. And we can see here that there was significantly more overlap taking place in the last debate between Clinton and Trump. And you can see that that amount exceeded 30% total for the 3 debates. And so the solutions we have are very good in trying to automatically assess that overlap. It's really helpful to detect that, both for training purposes for our algorithms, but also for trying to improve intelligibility, because there are options to try and separate out the audio when you have overlap. If you can suppress the overlapping speaker and just bring out the core speaker that you're trying to bring out for maybe education purposes, or for lectures, or for public speaking. Those are areas that you might see that. So another application where we see speech technology being used. Next, we'll also look at how we might apply this diarization and speech technology for an educational context. So we looked at using audio captured in daycare centers. And so this is audio that little children are moving around in different learning spaces. So there could be maybe a science type space or an art space or blocks or a reading book area. And so this would represent different locations that children might be able to move in an educational daycare type space. And what we wanted to do was to kind of assess where the children are moving to and where they're having interaction with their teachers. And so we used this Lena unit. 2 of our students helped found the technology that went into the Lena Foundation platform here. This was actually used in over 65 different countries worldwide. President Obama held this device up at the White House during his presidency to announce the 30 million word gap. That 30 million words represents the difference between how many words an 8-month-old infant hears going to 36 months if they have a rich language exposure versus a poor language exposure. So the goal for this device here is really to encourage more language interaction with young children to develop their language and vocabulary skills. And so here what we do is we capture the audio, but we'd also like to know where they're actually moving around in this. So there's a system called UbiSense. They're kind of small little RFID tags that are clip-on, so you can clip those onto the children, and as they're moving around in this space, we can track where they are. And so with that, we're able to now look for hotspots where we see communication engagement. So what's being shown here are different locations in that learning space and where the teacher to child interaction in terms of their vocabulary is most active. So in essence, one could look at your space here, and if you're trying to optimize your space for the best child to teacher interaction, we can see here that the large blocks area is not getting as much engagement. But the carpet area, which is maybe more reading, and some other areas, puzzle and music and so forth, they're having a little bit more interaction with the teachers. Okay, so this is important for looking at the space. In addition, we can also look at individual children and seeing whether individual children are getting proper language exposure on a daily basis to ensure that they're getting good instruction from their teachers. So it's not to try and judge the teachers, we're simply trying to ensure that the children are each getting the same level of interaction and support. So that's one of the domains. The last area that I'm going to talk about here is, well, we talked about maybe peer-led team learning. We've talked about the child space here and daycare spaces. Now we're going to move on to other team-based communication analysis, but now we're going to be looking at going to the moon. So this was an effort funded by the National Science Foundation. NSF saw the value in trying to preserve the audio that was from the NASA Apollo 11 program. The aspect that was critical here was also capturing that audio. So here we have communications that was taking place between the astronauts and mission control. in mission control, everyone that's sitting in here has a particular assigned duty, and they're responsible for kind of ensuring that part of the mission is actually going to be successful. When someone here needs information, they're able to talk to the backroom support staff for each individual position in here. And so if you ever saw the movie for Apollo 13, you may have seen someone walking into a room and dumping from a cardboard box a number of parts, saying, well, you have 2 hours to build an oxygenation purification system, otherwise the 3 astronauts are going to die. So that was an example of the backroom support team. These people are here to provide support, but they're never known. We don't see them, you don't know who they are. And at any Apollo mission, you're looking at roughly 500 people that are actually working and supporting the team, but there are only roughly about 25 spots that are here that are actually being recorded. So the system that records this is called SoundScriber, and it's a 30-track tape system that is used to record and pull the audio. This shows the communication that you might see for NASA, and our goal here is to capture or recover, if you will, that audio to try and look at the communications from mission control and all the support staff that might be providing feedback to help these people. Realize that the support staff here may not necessarily be in Houston or in either Johnson Space Center or Kennedy Space Center. They could be in other locations like NASA Langley in Virginia or NASA Ames or some other locations as well. So we're going to move forward here and kind of show this is mission control. The gentleman you see here it works for NASA. His name is Greg Weissman. He's overseeing communication systems. And there's only one of these playback systems called SoundScriber. And it was obviously built in the 60s. And so Greg's solution to try and ensure that there's proper tape tension while we're playing this back is to use this scientific device here called a bungee cord. Okay, this is the same type of cord that you use to put your luggage on your roof rack for your car. And he's using that to put tension on this. Not the best solution if you're actually trying to digitize a lot of tapes, but that's what we had to work with when we put in the NSF proposal. Unfortunately, when we put in the NSF proposal, when we went down to NASA, we asked, where are all the tapes, or where's everything been digitized? And they kind of pointed us to a back room here where all the tapes were stored, and they said, well, none of these tapes have ever been digitized, so you're on your own. Here's the SoundScriber system, so do what you need to do. And so we first looked at this and realized, well, we've got not that Houston we have a problem, but we do have a problem because we have a read head here that only reads one track. Each of these tapes holds 14 hours. To digitize this, you have to digitize it in real time. So literally it takes 14 hours to digitize one tape. I know that you're looking at me on this recording here, but if you can look on the screen there, you'll notice that I actually have one of the tapes in front of me here. This is actually a Gemini 8 tape that actually has Neil Armstrong, who is commander for Gemini 8, on this tape. And this was recorded March 16th, 1966. So this is the tape, and this is the analog stuff that we're dealing with here. So I know many of you out there may never know what this is because in your mind, everything is digital. But this is a case where it wasn't digital. So we had to come up with a solution to try and recover all of that audio. And the way to do that was to rewire this system. And we had to actually come up with a new reading head. So the read head here only reads one track. We ended up designing a 3-track head to do a test trial to make sure that we could swap the heads out. And then we did the unheard of thing of designing a 30-track read head that would actually read all 30 tracks at the same time. So we built a digitizing solution there. And again, we went down to NASA, hoping that NASA would have teams of scientists and engineers that would go and rewire this for us. And they again just pointed us to the system and said, there it is, do what you need to do. So you could see we actually have the UT Dallas logo here. We built this patch panel here. I physically rewired this myself, realizing that this is the only playback system. So I was actually with this student here, Tuan, who's one of our undergraduate students from UTD, who was with me and helping me in the rewiring process. And I told Tuan, this is my comic relief at this point. I said, if we break this, we're going to hop in the car and we're driving to Mexico, because we would have broken the only system to play back any of these tapes and they'll never be heard of. So we were fortunate enough that we could do the rewiring and be able to install this tape and get it functioning so we could start the digitizing process. So Tuan worked, sorry, I'll leave this back here. Tuan spent 4 months every day digitizing those tapes and made a huge commitment for us as UTD to kind of make sure that data was recovered. So moving forward here, once we get that audio digitized, we have to make it useful. So if someone gives you 10,000 or 20,000 hours of audio, you can't listen to it all. You need to be able to search it and understand where hotspots or areas of interest might be. So we developed a multi-channel diarization pipeline, so you could see all the communication takes place here. We have maybe all of these channels. There are 30 channels that are in there. From those 30 channels, we run a speech activity detector, extract acoustic features, look at overlap. Fortunately, NASA is really good at the overlap aspects there. People don't overlap on their speech too much. We look at primary, secondary speakers and cluster those speakers. Then we end up coming up with a full speech recognition solution to recognize all the speech that was spoken in this diarization scheme, and we output that to allow that metadata to be shared with the community. So we spent about a year processing 19,000 hours of audio to make that available for the community. And so these show some of the outcomes of that analysis. So looking at the communications, we can come up with something called a core diagram here. This explains the different types of communication engagements that might take place over time. So here we select a period of time, and here this portion of time here represents the capsule communicator, Capcom. This is the only person that's allowed to talk to the astronauts. This person typically is also an astronaut that will go up later on in his career. And you can see here that Capcom is talking quite a bit. There are times he's talking to Buzz Aldrin, and times maybe that he's talking to Neil Armstrong here or Michael Collins. So we can see who they're speaking with. We can also see there are times when it looks like they're not really talking directly to someone. Here it's just they're speaking and maybe just giving information of what's going on as general knowledge. So the nice thing here is it gives us opportunities to listen and see how the communication engagement is taking place. So I'm going to play two examples here. One is Buzz Aldrin, and Buzz is talking back to NASA, and he's looking out the capsule window there and he sees Earth. The unfortunate thing is he sees nothing but water, so he's making a request back to NASA.
Hey Houston, you suppose you could turn the Earth a little bit so we could get a little bit more than just water?
Roger, 11. I don't think we got much control over that. Looks like you'll have to settle for the water.
All right, so that shows maybe Buzz Aldrin's sense of humor there. He was obviously hoping that NASA might be able to rotate the Earth a little bit so he could see some land, and unfortunately that wasn't possible there. So I can't let you go here without actually playing probably one of the most famous recordings that certainly came from the moon.
I'm at the foot of the ladder. The LEM footbeds are only depressed in the surface about 1 or 2 inches, although the surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. Ground mass is very fine. I'm going to step off the LEM now. That's one small step for man, one giant leap for mankind.
All right, so that was obviously Neil Armstrong. You could dispel any myths. He actually did walk on the moon, okay? Buzz Aldrin did as well. And it was one small step for man, one giant leap for mankind. So I know people think they may have said something else. A lot of our analysis, we can look at conversational turns, word counts, we can look at topics of conversation. We can also assess the sentiment, the emotional levels and stress levels of people's voices in the communication here. So it adds a lot of dimensions in this space. Here is an example of sentiment. We looked at the 3 astronauts over the entire 8-day mission, 195 hours, and we assessed their sentiment, neutral, positive, or negative. And you can see they're pretty much positive most of the way. A couple of times, maybe some negative, some technical problems here, maneuver that was particularly difficult to overcome. And so a couple of spots here where the sentiment was negative. It's not saying they were in an argument, but just areas where things may not have been as positive. So this was the entire mission for Apollo 11. Imagine what this might look like for Apollo 13, which obviously had way more challenges in that space. So this is one of the directions we're looking at now. Another thing that we can look at is, well, when we first captured the audio, we had lots and lots of people coming back to us. We released the audio to the community. We had a number of folks come back saying, hey, my uncle, my grandfather worked for NASA. We thought, well, it would be a kind of a cool thing if they could give us a picture of their uncle or their grandfather if they're still living, if not, just what their picture would be. And what we would do is we would go back to the full 19,000 hours of audio we've recovered and find all examples of where that person spoke and put a permanent location where someone could go and listen to just their relative engaging in the NASA program, or at least in the Apollo 11 mission here. And so we call this Finding Waldo. So now we're looking at pulling all these together. A couple of the speakers that we've identified clearly was the flight director and also Capcom. So this is Charlie Duke. He was the capsule communicator for Apollo 11. But Charlie Duke obviously was also a moonwalker and walked on the moon for Apollo 16. Here he is more recently, and Charlie obviously visited UT Dallas about a year and a half ago, 2 years back, for the Back to Space program as one of our visitors here for UTD. So the Finding Waldo program is something we've got a big effort in. Another thing we did is we released all the audio for the community, and this is primarily the speech technology community, but also for historians, for archivists, and people that are interested in history. So this way they could get access to the audio. Quite frankly, we're looking at trying to analyze as much as possible the backroom discussions. We're still hoping that we can find a few of those hidden figures. Margot Shatterley's book and a number of people that work behind the scenes included also a number of the hidden figures. We have not found them yet, but we've only looked at Apollo 11 so far. So this is a challenge we're looking at. Right now for this Fearless Steps challenge for 2018-2019, we've released this to the community worldwide. We've had 160 different academic and corporate type groups worldwide that have received the audio and have participated in this speech technology challenge for different speech processing schemes. And so we announce winners each year for this. So this is an outreach effort to try and help people in the speech technology space. We're also looking now at historians and archivists and STEM educators to see if we can kind of transition the audio to help them for educational purposes. We've been featured in 40 to 50 different TV, radio, news, broadcasts for Apollo efforts over the last maybe 3 years. And we're particularly wanting to recognize these three individuals here. Lakshman, Abhijit Sanwan, and Chengzhu Yu are the two PhD students and one research scientist that were instrumental in doing a lot of the work to recover all the Apollo 11 type efforts here. So the big, probably visible thing that happened with this audio is that we were contacted by CNN, and they were trying to actually put audio to a lot of silent film that NASA had recorded. NASA had lots of silent film that was recorded during the mission, but they were 70 millimeter silent film. And what CNN was trying to do was to read the lips of what the person was saying and then go ask NASA, can you find that audio for us and let us stitch the audio together? And they said, well, we can't do that, but go find this group at UT Dallas. They've been doing work on this and they could help you. And so we provided all the audio plus all the diarization, text, speaker ID tags to a CNN movie studio. Next day, they came back with some video that was just truly remarkable. So I'm going to show you that on the next slide here. So the video here, this is Charlie Duke, the capsule communicator. And what you're going to see here is a video clip There was originally completely silent video that took the audio that we captured and recovered from the tapes, and they were stitched together. Now, pay attention here. You'll know that this audio is not from the video recording, because if you were videotaping someone talking, you would only get their side of the conversation. And if you're listening to this, you'll hear both sides of the conversation.
Complete with 1 star.
Contact now. Start getting shut off. No. Tell contact now. Go. Hey, John, you think you drove that antenna to the stops?
Probably.
Want him to make sure, check the breakers?
Yeah, we can have him confirm those breakers. Sure, Chuck.
So you can hear the audio there is continuous. The video is only in certain blocks, and that's because the videographer that NASA had at the time only took short, maybe a 5-second video of one person and someone else, and so it was just randomly stitched together. All of that was actually used to put audio to all of the silent video that CNN had. It was used for the CNN movie that was broadcast, or was in movie theaters, but also broadcast 3 times nationwide here in the United States. In addition to that, we've had a whole series of undergraduate senior design teams that have been involved in promoting and developing outreach type efforts for our webpage, the Explore Apollo webpage. They also participated in Engineers Week at the Perot Museum every February. All the students would bring them down. They would go through and do demos for anywhere from 800 to 2,000 children that are part of the Engineers Week effort there. So we do a lot of outreach on that side. This is the web page. So if you have interest in kind of perusing any of the audio from Apollo 11, you'll be able to go see this here and listen to it. We also have lots of images that are synchronized with the audio, so you'll get different events. One of the things that the students wanted to have was this little spot here that says surprise me. So you click this and it'll put you into a random thing that might have happened during the Apollo 11 mission. NASA didn't really like the button that says surprise me. They don't like surprises, but we did actually have that as one of the options there. So this actually right now supports Apollo 11. And so we've also done outreach to the Dallas community. So we participated in the work that Congresswoman Bernice Jonsson organized with UT Dallas in 2016. So this was an outreach for a magnet school here in Dallas. We gave talks on work that we were doing for Apollo. And at that particular meeting, there was a live satellite uplink to the International Space Station. And so we had live question and answer that took place with the 2 astronauts. One was British and one was American that was at the space station at the time. So again, right now, NASA is feeding us also audio from the International Space Station, so we're applying analysis to that as well. So one of my last slides here is simply to say, you know, in looking at this audio, the audio from Apollo it's more than just people talking. They're actually accomplishing probably one of mankind's most technologically challenging tasks that people have dreamed for many, many years. The capturing of the audio was important. NASA, you know, if you look at this tape, this yellow sticker actually says moon landing here. That was how they documented which tape had the moon landing. And being able to pull this off now in a digital format will preserve this for eternity. The problem is it's only Apollo 11, and we've got some of Apollo 13, but the rest of the Apollo missions are still there. So that means there's more than 150,000 hours of audio that's there. All of these tapes are 50-year-old. The likelihood that they'll survive into the future is limited. And so we did put in a request to NSF to see if we could get additional funding. And last month, we learned that we were awarded an additional $1.2 million from the National Science Foundation to go back and recover the remaining Apollo data, 150,000 hours, and also to apply all of our diarization advancements to help this. We are advertising and looking for a postdoctoral researcher. If you want to actually come and have a part of history, you can do that. And we're actively recruiting undergraduate students to be part of senior design teams to help in the digitizing process of this. It'll take 3 years. We will ensure that you have great support, and no student is going to be working more than 2 weeks at NASA digitizing tapes. And the requirement is you have to get a picture next to SoundScriber, because we want to have a nice wall of pictures of all the students from UTD that helped recover and preserve history here. Okay, so that's that part. My closing 2 slides here. We've covered a lot of things for the Center for Robust Speech Systems and the research that I've worked with in my career. None of this, none of this is done in a vacuum. The reason we do this is for education and to train and hope that our students learn and be able to make an impact to society. So our PhD students, these are the 51 PhD students that I've supervised in my career, about 38 of them from UT Dallas here. They've had enormous impacts in society. One of our students, Nan Kumar, he's now branch chief for the Food and Drug Administration. He oversees all of communication assist devices for the United States in assessing their availability and performance. Rui Sarakaya worked at IBM, then moved to Microsoft. He oversaw and built the team that constructed Cortana, which is the speech recognition engine that Microsoft uses. He got hired away to go to Amazon, and so now he's the chief scientist for Amazon AI, overseeing Alexa. So kind of imagine the stuff that he's doing there. Another individual I'd like to point out is Bowen Shao. Bowen worked for IBM for many years, built the speech-to-speech translation systems that are used for first responders worldwide. His speech-to-speech translation systems run on small smartphone systems and support 35 language translation simultaneously. So if you're sending someone to, a earthquake location in Turkey, they're more than likely using an IBM platform that Bowen developed. He now is vice president for JDAI in China, a company that had $65 billion in sales last year, overseeing their entire AI program for voice engagement for JD. Huge engagements there. I'll also point out Abhijit Sanwan, one of our top PhD students and research scientists, instrumental in really helping navigate all of our work on the Apollo efforts, and just monumental in the work that he's done. I can't go through all the students, there are just too many of them, but all of them, have been trained here. We set them on a path, and they've gone out to make great contributions to the field. In addition to the PhD students, we also have a really large number of master's level students that have also had big impact in the field. So we're really appreciative and recognize that without these students, we're just faculty kind of trying to bring in grants and get things going. Without the students, this is where we kind of make our progress. So I'll close there by thanking everyone. I thank our research sponsors, particularly I thank the U.S. Air Force Research Laboratory. They've been our primary sponsor for the last 15 years, provided extensive support for many of our students, the National Science Foundation, NIH in particular, a number of the agencies, Air Force, Army, Navy, the intelligence agencies as well, and many industry sponsors as well. So we're really appreciative of all their support. Know that all of the funds that we receive all go to support students and hopefully direct them in a path that allow them to go out and make a difference in the world. So I'll stop there and thank you very much for your time.
You do have a few questions in the queue. Would you like to go ahead and address a few of those?
Yes, let's go ahead with those.
Excellent. All right, the first question is, could the driving app technology be used for future self-driving cars?
Yes, absolutely, because one would expect that when you look at self-driving, the driving process goes anywhere from 0 to 5. Those are the levels. And at level 0, that's where you would expect to be for fully manual driving. Level 5 is fully autonomous. You could be sitting in the back seat. And so most people don't have much of an understanding of how to actually go from fully manual to fully autonomous. And so that's the real challenge that exists in self-driving. So using the driving app, one could certainly try to model when the driver is actually having problems. You can actually use that driving app to assess the automatic driver, and if the automatic system starts to have problems, one could attempt to try and switch from automatic to manual, be able to determine whether the autonomous vehicle is actually driving in a risky manner. I know that sounds odd, but that's possible. So,
absolutely, that makes perfectly clear sense. Another question that is in the queue related to the driving app is as follows. Could the driving app also help with making a virtual driving class, or is it solely for monitoring a person driving?
So the driving app was primarily for data logging and data capture. So it was primarily used to try and capture when people, as a way to emulate a instrumented vehicle. So one could clearly use this for teaching driving. One could come up with, you can add that on to a driving simulator, and then be able to monitor how the person is driving in real life. So the biggest risk when I've looked at talks I've been to on driver modeling, when you look at instructed driving, like a son or daughter, when they're driving, the parent is usually the person sitting next to them that's actually giving the instruction. So what happens is the risk factor, once a driver goes from kind of supervised driving to independent, that first 2 to 3 months is the biggest risk factor. And so that's where we would expect to have a high risk domain. So having the driving app on the student's smartphone will allow you to kind of monitor and characterize and give feedback to the student when there's a problem.
Excellent, thank you. An additional question is, you mentioned about how the audio stream analysis can identify accents. Does the program need to store that? And if so, how does the program store these different pronounced syllables and mark them as the same sound?
So what we would look for is if someone is having a particular accent, then we would look at the variability of how the person speaks. And so the wide variation there is where you would actually see pronunciation variability. So looking at some words like multi-syllable words that are longer in duration typically have less pronunciation variability. Short words that are more joining words tend to have much more variability. And so being able to look at more complex words allows us to maybe assess accent characteristics in a more clear way.
Perfect. Thank you for your response. It looks like we have another question. This may be a very simple answer. Please, can you quickly go through the different open source code that you share?
Okay, so yeah, so if you're looking for open source, let's say on the CCI mobile research platform for the cochlear implant space, we have all kinds of tools that are involved for that setup. That includes sample templates where people can develop their own software. The other represents actual tools that will run on the research platform and allow you to kind of interact with the cochlear implant setup. So all of that code is open source. It's sitting on GitHub, and it's free to be downloaded by anyone who wants to have access to it.
Excellent. Thank you for sharing that. The final, oh, no, I don't have a final question. I believe I have 2 more. What does the driver app use to monitor driver behavior? Does it need installation of any cameras and sensors?
Yeah, that's a really good question, because when you look at an instrumented vehicle, a lot of the research in the field was done with instrumented vehicles. And the problem with that is that you're driving a car that's not yours. So what we did is we migrated off to smartphone, and the advantage that has is that you're now driving your own vehicle. So what we're actually doing is we're using roughly about 30 different types of sensors that are built into the smartphone or your tablet that actually look at the gyroscope, accelerometers, and so forth that are in your smartphone. And we've done work on trying to, so to make the answer, you do not have to connect the phone to anything else. Once you download the app itself actually will allow you to be able to monitor and characterize the driving behavior just from the phone. The issue is that you may have to, I don't know what the right word is, but be able to characterize or offload the data out. So right now it's set up where you have to actually you have to actually pull the data off to analyze it. So we don't have the system running right away that allows you to make the detection up front that the person is distracted or not.
Excellent. The next question is, please can you elaborate on any cognitive load aspects you may have discerned from the audio signals?
Yeah, so we've done a lot of work on speech under stress, and so looking at assessing stress levels in someone's voice is a core aspect there. We've done this for the U.S. military. I've listened to literally thousands of hours of air-to-air and air-to-ground communications by NATO pilots over Bosnia and Serbia, for example. And so being able to assess stress and cognitive load factors are a core thing for the field, and something that will be critical in being able to move speech technology forward to assess speaker traits in the communication context.
Perfect. Thank you very much. At this time, there are no additional questions in the queue. Thank you, Dr. Hansen, for sharing your time, talent, and resources with the attendees and community at large. For additional information and Office of Research events, please visit research.utdallas.edu and have a nice afternoon.